Great. Welcome back to the final hottest talk of fall 2024. We're very happy to have Paige North, who will tell us about coinductive control of inductive data types.
Indeed. Well, thanks a lot for having me at the hottest seminar. Very excited to be here. So I'm talking about, as Emily said, coinductive control of inductive data types. I will say in a second what the basic idea is. First, I want to say that this is joint work with Maximilien Péroux, who was my co-author on the first paper, and Lukas Mulder, my recent master's student who helped us with the second paper, and also some work in progress that we're working on. So here's the outline, which you can also see at the top of the slides. So I want to, in this talk, give the theorem statement, which looks a little bit complicated, and then explain it by giving an example and kind of working through what it means in an example. So let me read through this. So the category of algebras of an accessible black symmetric monodal endofunctor. So we're thinking about endofunctors on a category. And we have these, I put them in italics so that maybe you can kind of squint and ignore them a little bit, these hypotheses. When we have such an endofunctor on a category that we assume is locally presentable and symmetric monoidal closed, then we find that the category of algebras of that endofunctor is enriched over the category of coalgebras of the same endofunctor. So that was the content of the first paper where we proved this for like a fixed category and a fixed endofunctor. And in Lukas's master's thesis, which will be the subject of an upcoming paper, we did some pretty extensive category theory to just parameterize the statement and in the functor f, still for a fixed category C, and show that we have a functor from the category of such endofunctors on C to a category of enriched categories. Okay, so I will say in a second why we're interested in endofunctors, but we're in the hottest seminar, so hopefully that people already have an idea. So the examples that we're interested in are motivated by type theory and functional programming. So in particular, we're interested in polynomial endofunctors. If you don't know what those are, we'll give some examples and explanation. But often for these examples, for these endofunctors to fall under our theorem and its hypotheses, we need to assume some extra structure that corresponds to this hypothesis of being black symmetric monoidal. And yeah, so the point of the paper was to exhibit this enrichment, but then we try to give some reasons of why this is useful information to have, to know that the category is enriched. And so we describe how one could generalize the notion of initial algebra, which is important for the semantics of type theory and functional programming languages, as most of us know. And those are sometimes called W types or inductive data types. Okay, maybe before I move on, I won't say so much of this in the rest of the talk, but I mean, I will maybe just explain these hypotheses a little bit. So we're talking about enrichment of categories. So we need something to be symmetric monodal closed to get off the ground in terms of that kind of theory. And we also want the functor to be lax symmetric monoidal so that, yeah, so that our category of coalgebras is symmetric monoidal, and then we can enrich in that. And we also assume that the underlying category is locally presentable and that the functor is accessible. And this makes it so that all the categories in sight are locally presentable and that we can just apply the general adjoint functor theorem whenever we want. And that's kind of the technical tool that we're using all the time to prove the theorems. Okay, so to now start giving some intuition about what this means, I want to go back to the original works along these lines. So we're thinking about endofunctors and algebras for endofunctors and coalgebras for endofunctors because for category theorists who are interested in the semantics of functional programming languages. Back in the day, in the 60s, Sweedler, who you might know, wrote this book about Hop algebra. He defined what he called a universal measuring coalgebra. So he was considering algebra in the classical sense. So for K is the field, everything about algebra is over the field, A and B. he defined a K coalgebra that I don't think he noted like this, but I'm going to note it like this in the rest of the talk, so we'll keep the notation consistent, that he called the universal measuring coalgebra. And though he didn't use this language, Wraith, I think in the same year, recognized that underlined an enrichment of K algebras in K coalgebras. And from this coalgebra, you can extract, in particular, the set of so I'm using this notation to note the HOM here. So this is the category of algebras. So this is the HOM of algebra homomorphisms, or the HOM set of algebra homomorphisms. And so this is the enriched HOM, the enriched coalgebra homomorphism object, let's say. And I want to say that we can extract the elements of this guy from this guy by, in the language of Sweedler, looking at the set-like elements, or he also called them the group-like elements, which are those of this form. So this is not so important for this talk because this is a different setting, but I just want to connect it with what he did. So he can extract the algebra homomorphisms from this coalgebra, and then he describes, and I will describe in our setting, a similar point of view, how the other elements in the underlying set of this coalgebra describe partial algebra homomorphisms from A to B.
Okay. Can I ask a question about this? So yeah. I'm wondering if this tells us that the underlying category of the enriched category is the category of algebras and algebra homomorphisms. So in other words, our set-like elements maps out of the monoidal unit in coalgebras or something.
Yeah, exactly. Yeah, I'll say that more precisely for our theorem. Exactly. Okay, and then just to connect this with something that people might have considered or heard about, I don't know, in your algebra class in undergraduate, you can take the B here to be the ground field K. And if you look at this measuring coalgebra into K from an arbitrary algebra A, then you get the dual of A, the Sweedler dual. So that's something, I mean, that's something that's a little bit more prominent than the notion of measuring coalgebra that people might have heard of. Okay, so that's the original thing. Then there are many, many analogues that have come up. So I've given similar talks to this before, and in the first version, this list was very short, but as I've given the talks, people have told me about more and more instances. Yeah, so people have shown that monoids are enriched in comonoids here, that modules over monads are enriched in comodules, that DG algebras are enriched in DG coalgebras. Here again, monoids enriched in comoids. I think these two, these people didn't know about this PhD thesis. Actually, I only heard about it recently. I think it was a bit lost to time, but they kind of generalize and specialize in different ways. So I wanted to list both of them. Vasilikopoulou shows that V categories, so enriched categories, are enriched in enriched co-categories. Then my co-author showed that infinity algebras of infinity operas are enriched in the corresponding co-algebras. Here, interestingly, monads, they're showing them to be enriched in comonads, also with applications to programming language semantics. And then in our paper that I'm talking about, we're talking about algebras of endofunctors being enriched in coalgebras of the same endofunctors. And then preparing for this talk, I found these two papers. They're both from 2024. This one is about stable anti-Yetter-Grinfeld modules being enriched in the co-version of that, but I don't know what these are. So I won't say anything more about that. And also modules in a double categorical sense being enriched in comodules. Okay, so one thing I want to say about this, or one point I want to make in this talk, is that this paper is an instance of a more general phenomenon. It'd be interesting to understand if it's possible to prove a more general theorem, of which these are all examples. But this is an instance of a more general phenomenon. So I want to advertise to all of you people, whatever algebras you're interested in, they are probably enriched in some corresponding notion of coalgebras. So it'd be interesting to think about that. Yeah, if you have some favorite notion of algebra. But also I want to say, of course, this is the hottest seminar, and this talk is not very much about hot. This is more about just general functional programming languages and inductive data types, which are of course important for HOT, but not a special feature of HOT. But there must be an analog for about higher inductive types. The challenge, I think, would just be formulating that well enough to apply the kind of machinery that all these papers apply. Okay. Yeah, so I want to say a little bit about inductive types. I mean, this is the hottest seminar, so probably most or everybody knows about this, but just in case, hopefully there are people listening who are new to this field. I want to, say something about what inductive types are. So when we do functional programming or type theory, most of the types that we're working with some important exceptions, are defined inductively. And in terms of category theory, that means that we're looking at a polynomial endofunctor and the initial algebra of that, which we think of as the meaning or the categorical semantics of the inductive data type, and often the vocabulary W type is used in that context. So there are two basic examples that I want to mention. So there's the natural numbers example. I think everyone's favorite example, my favorite example, and the running example in this talk, also in the first paper. So when we define the natural numbers in type theory, I'm not writing any type theory syntax here, maybe I should have, but the language of this talk is category theory, so I'll just stick to that. So we define the natural numbers. We think about the endofunctor, usually on set, that takes an object x to x plus 1. So the plus is the coproduct and 1 is the terminal object, the singleton. So we look at the category of algebras. We take the initial object, that's the natural numbers. And the fact that the natural numbers is the initial object of this endofunctor corresponds to the fact that the Peano axioms define the natural numbers uniquely. So that's something that's very old, going back to Peano. Then we can ask what the terminal coalgebra is. Maybe I should define the words algebra and coalgebra in a second, but if we look at the terminal coalgebra, so we take the category of coalgebras and look at the terminal object, it's what I'm calling an infinity, which might not be the greatest name for it, but it's kind of the one-point compactification of the natural numbers. So it's the natural numbers plus a point at infinity. I'm using the word compactification, but it's just a set. And this functor, this endofunctor, does satisfy the hypotheses of our theorem. So I'm going to use it to illustrate the theorem throughout the rest of the talk. And let me just back up and explain what an algebra and a coalgebra is, just in case wasn't clear. So we're looking at this endofunctor that sends x to x plus 1. And an algebra is a map, is a function from, well, an algebra, let's say, first is a set x, and then a function from the value of this functor on x, so x plus 1 to x. An algebra here is a function from x plus 1 to x. So it's like an algebra for a monad, but we don't have any commutative diagrams that we're asking, or diagrams that we're asking to commute. And dually, a coalgebra for the same endofunctor is a morphism, is a function from x to x plus 1. Okay, and then maybe the second favorite example, the second more complicated example is lists, which directly generalizes the natural numbers. So if we look at lists with values in a set A, then we're thinking about this endofunctor, also usually unset, that takes a set x to 1 plus a times x. So this represents, I should have said here, maybe this represents the 0, this kind of inductively generates for us the 0 of the natural numbers. And this gives us, this represents the unary operation on the natural numbers, that is the successor. Okay, so here, this 1 represents the list with no elements, nil. And this represents a kind of operation that we can do on lists that takes in an element of A and an element of X, which when we're looking at the initial algebra will be lists, and produces a new list. So it takes an element of A and an element of X, which we're often thinking of as the set of lists, and produces a new list. So it just appends the element of A to the old list to produce a new list. Okay, so we look at this endofunctor, we look at the category of algebras, then we look at the initial algebra, the initial object in that category, and that is the set of lists with entries from A. And then if we do the dual thing, we take this endofunctor, we look at the category of coalgebras and then the terminal coalgebra. That's the set of streams. So people use different terminology for this terminal coalgebra. Some people call them co-lists. I'm saying streams. And those are like lists where lists are finite. So we can have the empty list, we can have a list of any finite length, but a stream can be also infinite. So the lists are a subset of streams, and the streams can also be infinite. So the streams have the same relation to lists as this extended natural numbers have to the natural numbers. And indeed, this example generalizes this example where A is a singleton. Okay, so this endofunctor also is an example of our theorem. But like I said in the first slide, we need often to make some extra hypotheses of having extra structure to make the functor lack symmetric monoidal. And here that amounts to asking for a commutative monoid structure on the set of values A. Okay, but I'm going to focus on this this example of the natural numbers in the rest of the talk, and that's why I've put it in this red box so that it's clear throughout the rest of the talk. When I'm talking about the specific example, it will be in a red box, and when I'm talking about general things, it will be in a blue box. Okay, does anybody have any questions so far? Okay, so now I want to talk about the actual paper that we wrote. That was all background. So we first, I kind of want to move from the machinery, the theorem that and the definitions that we made in the paper to like what it actually means, like tangibly. So here again, this is kind of complicated, I think. And I'm going to explain slide by slide. We're going to break this down slide by slide to something more tangible. Okay, so we define this measuring coalgebra in the following way. So we want to fix a category and an endofunctor that satisfy our hypotheses for the rest of this talk. And we're going to find what a measure is first. So we have two algebras like this, and we want to define this measuring coalgebra between them. So first we define just a measure which is slightly more general. And it consists of a coalgebra. So we're not talking about the universal measure so far, but just a coalgebra that measures, in some sense, the homomorphisms, algebra homomorphisms from A to B. So we do that by looking at here the internal hom from A to B and C. So we're assuming C is monoidal closed. So I'm using this underline notation to mean the internal hom in C between A and B. So we're looking at this internal hom, so this is object in curly C. And we're looking at, let's say, C indexed morphisms. Unfortunately, I've used the letter C multiple places, but C indexed morphisms from A to B in curly C. So C index, indexed by the coalgebra in the category curly C. Okay, so we're looking at C indexed morphisms just between the underlying objects in curly C, not taking into account yet the algebra structure on A and B. But now we do that by asking that it satisfies the commutativity of this diagram. Okay, so the commutativity of this diagram is a bit complicated. You might ask me why this diagram. I think I could explain it in a slightly slicker way at the end of the talk, but right now I just want to say that if you just think about all the data that we have in this part of the definition, so the alpha, beta, the chi, and the phi, how you might ask those four things to cohere, this is the diagram that you can write down that relates them. So we ask that this diagram commutes, and maybe I should say this unlabeled arrow is the lax monoidalness of F. That's part of the structure. So that's a measure. And then we ask that we have a category of measures in the obvious way. And then we look at the terminal measure that in some sense kind of, because it's terminal, we can maybe think that it kind of includes all the possible coalgebras that can be mapped into this hom object with this property. And then we call it the universal measure. Okay, so that's the definition.
Just to keep track of where we are, we have not yet built a coalgebra structure on CAB. Is that correct?
Yeah, so we don't have a coalgebra structure on this, and we're not going to do that.
Right.
We are just
I mean, if we
looking at,
did
like,
have one, then I think that might be the terminal measure. Is that right? With the identity
Yeah.
or something?
yeah, definitely.
So this is a way to reason about that in the absence of such a thing. Something.
Yeah. Yeah, I think so. Yeah, so we just look at, like, yeah, I mean, I'm not totally sure like how you would build in the community of this diagram to that. But yeah, so we're just looking at, like, yeah, definitely the terminal measure, the universal measure, like, captures kind of the biggest image here. It kind of is like kind of the union of all the images of all the possible coalgebras that can be mapped into this hom object. Yeah. Okay, so to just rephrase our theorem now that we have some more vocabulary, we prove that the universal measure always exists, and that these are the Hom coalgebras of an enrichment in the normal category of algebras, in the normal category, I'm using normal in a non-technical sense, normal category of coalgebras. So this is what Emily asked. When I use the word enrichment, I mean that we have an enriched category, enriched in coalgebras. And when I take the points, like when I take the underlying category, I get back the original one, the algebras. So we're getting strictly more information. I mean, I guess we could have the same amount of information at this point, but I would tell you that we have strictly more information in the enriched category than in the underlying normal category of algebras. Okay. So now I want to start breaking down the definition of measure, which was pretty abstract and kind of unclear, like what exactly that's telling us about the relationship between algebras A and B in the example of the natural numbers. That's why this is red. Okay, so we're asking for what we're starting with, let's say, algebras A and B. So now again, remember, okay, we're looking at the endofunctor for the natural numbers. So in particular, our underlying category is set, so everything's just sets and functions here. So we have algebras A and B, and we wanted to kind of read through the definition of measure now in this example. So it's a coalgebra C together with a function like this. So we're in set, so the internal Hom is just a set of functions here. So we're looking at C, I'm thinking about this as C indexed functions from A to B. Such that that diagram commutes, but now because we're just in set, I'm just going to think about what it means pointwise. So if we think about that for, I don't know, 5 or 10 minutes, then we find that the commutativity of the diagram is just these 3 requirements. So I should have written here, I should have called this function f. That's what I'm using here. And I'm writing the values of C here as subscripts and the values of A here as these normal inputs. Okay, so first we ask that f sub C takes 0 to 0. So whenever I plug in a 0 here, I get the 0 here. And by 0, I mean, so remember that we're looking at algebras of the endofunctor takes x to x plus 1. So we always have a special point because algebras are functions from x plus 1 to x. So we always have a special point that's the image of 1. So that's the 0. And I'm also using the plus 1. So we have a function from x plus 1 to x. So in particular, we also have a function from x to x, this thing that we usually think about as plus 1 in when we're in the natural numbers. So I'm writing that algebra structure as plus 1, even in an arbitrary algebra like A. Okay, so we have to send 0 to 0 always. We want to send the successor of anything in A to 0 in a particular case. So again, this is some notation. So we're in here the example of the natural numbers. So I'm looking at arbitrary coalgebra C, but I know what the terminal one is. It's this n infinity. So there's, of course, a universal function from C to n infinity, universal coalgebra map that's in particular a function. So it will tell me, it will give me a number, a finite number or infinity for any C in C. And I'm writing that as this bracket. And I might say it out loud as the index. And that number is measuring something. So if we think about, again, what a coalgebra is, it's a map from x to x plus 1 that we can think of as a partial endofunction. So when I have a partial endofunction on x, I can ask how many times do I have to apply that endofunction for it to not be defined? The minimum number of times I should apply that for it to not be defined. And that's what this bracket is telling me. So if I have an element of my coalgebra with index 0, meaning that it is the value of the partial endofunction is undefined at C, then I should send this guy to 0. Okay, and then we have the last one, which I think is the most interesting one. So if we just cover up this little c and the little c minus 1, the subscripts, then this looks like, well, this one and the first requirement look like normal requirements for an algebra homomorphism for this particular endofunctor. But it's being kind of twisted, let's say, by this -1 action. So I want to say that if I want to know what the value of an arbitrary f sub c is at a successor, then I should not, like in the normal algebra case, just look at the value at the original guy plus 1, but I should look at the value of the original guy, not at f sub c, but at f sub c minus 1. So there's kind of a twist happening there. Okay, so the commutativity of the diagram from the previous slide is these 3 requirements. And then again, I just say the universal measure is a terminal such measure. Okay, but I think it's still not clear what kind of information is being captured by this universal measure. So we're still gonna try to break it down. Okay, was there a question in the chat? Good question. Okay, someone asked me what c minus 1 is. Yeah, so I didn't say this explicitly. So I said what 0 was, what plus 1 is, what the index is, and then the c minus 1. So like I said, when we have a coalgebra, that's a partial endofunction. And when we're thinking about the terminal coalgebra and infinity, that partial endofunction is doing -1 in the normal way. So I just want to write -1 in any coalgebra just to denote the application of the partial endofunction. Thanks a lot for the question. Okay, hopefully that's clear. All right, so I said that in the traditional, the first instance of this phenomenon by Sweedler and Wraith, Sweedler was looking at the group-like or set-like elements of the universal measuring coalgebra and extracting or identifying the particular ones. He was looking at the universal measuring coalgebra and the group-like elements inside of them, which were the normal old algebra homomorphisms. So we want to say the same thing. This is also kind of what I said quickly when I said that we have an enrichment of the category of algebras and coalgebras. What that means is that when we take the points, which are functions or morphisms like this, then we obtain the set of the hom sets in the underlying category, which here are the algebra homomorphisms. Okay, so it's just baked into our theory, I guess, that we have this fact that when we take the set of morphisms like this, we get this set. And now I want to, well, I would say some things before that, but I want to calculate this in the category of natural numbers in the next, or in the example of natural numbers in the next slide, so we can see like exactly what's happening. Okay, so just to say this in slightly different words, the points of this, which I'm sorry, this should be underlined. The points of this measuring coalgebra are the algebra homomorphisms. And now I'm starting to use the word total because, like I said at the beginning, I'm going to argue that this guy looks like a collection of partial algebra homomorphisms. And we're most interested in their example in natural numbers, which is endofunctor on the category of sets with the Cartesian monoidal structure. But always when we are looking at endofunctors on this monoidal category, the underlying set of this unit in the category of coalgebras, so we put a monoidal structure on the category of coalgebras, and the unit always has underlying set the singleton. So always when we're looking at this particular category, these points here are some kind of special elements of this measuring coalgebra. Because they, as a function, they're just points, they're just elements. But as a coalgebra morphism, they're telling us that they're elements that behave in some particular way. Okay, so let's look at that in this example of natural numbers. So we want to calculate exactly what the points are here. So in this example, like I said, the monoidal unit in coalgebras has underlying sets of singleton. But now we, in this particular example, can say what the coalgebra structure is. So when I say -1, I'm talking about the application of the partial endofunction that constitutes the coalgebra structure. But here I'm saying that the coalgebra structure just takes the point to itself over and over again. So in particular, maybe I can say that to tie it back to what I said previously, if we take the index here, that is the map from this guy to n infinity, the value of this point is infinity because it's always being taken to itself. It's never undefined. Okay, so if we look at points in here, that is maps from this guy to this guy, they are elements of this coalgebra that are always taken to themselves by the partial endomorphism that constitutes the coalgebra structure. Okay, so that's what I said. So these points are elements in here that are always taken to themselves. And then if we look at the definition of measuring here from before, so there are some irrelevant parts that I've blocked out, and I've added in here just the relevant parts. We're asking that for all C and C, so this is our C now, and this is our little c, we have this. So f sub star of 0 should go to 0. And here f sub star of a plus 1 should go to f sub star minus 1, which is a star of a plus 1. So I'm going to replace all the subscripts with stars because star and star minus 1 are both star. There we go. So now we see that the definition of measuring collapses in this case to the specification for just a regular old algebra homomorphism between two algebras of this endofunctor. Okay, so now we've calculated that the morphism from A to B that corresponds to such a point is a total algebra homomorphism. So it's an element of this set, the Hom set of the underlying category. Okay, so now I want to do some more calculations to further explore the structure of these measuring coalgebras. And so I'm just gonna pull some facts out of my hat. Well, the first one we probably all know. So I want to look at now the whole set here. So I've identified some elements in this set, which are the set-like elements that represent the total algebra homomorphisms, but now I want to understand the whole set. So when we're looking at the unenriched case, just of normal algebras and algebra homomorphisms, of course, we know that since the natural numbers is the initial algebra, by definition, this Hom set is a singleton. But now in the enriched case, I'm not going to do this calculation. I'm just going to pull it out of my hat, as I said. If I calculate the this coalgebra from n to a for any algebra a, I find that it's n infinity. Okay, and like I said, we expect that when we take the points of this, we find this. That's what the previous calculation told us. And indeed, there's one point of this coalgebra, which is the point at infinity. It's the only point that's being taken to itself by the coalgebra structure. So that's how we end up with this guy. Okay, but if we look at this coalgebra in particular, its underlying set, it has this one point at infinity, but it has all these other points. So what is that? What kind of information is being carried by all those other points, all those other elements? That's the question now. Okay, so again, that's the question. I have here this fact from the previous slide. We have this. We want to understand what all the elements of this set are. So let me denote them by f sub 0, f sub 1, ... f sub infinity. We know what f sub infinity is, kind of, from the previous slide. Now the question is, what are all the other ones? Okay, so if we now, again, look at the definition of measuring for each of these. So first let's start with f sub 0. Then there are some irrelevant parts again, but I have recalled here the relevant parts. So if we look at, so what was the first requirement that was saying that we want to always send 0 to 0. And it was the second part that said that if this guy had index 0, it does here, that we want to send every successor to 0. So everything gets sent to 0 by f sub 0. Okay. And now we want to know what f sub 1 does as we're thinking of them as functions from n to a. So we recall the definition of measuring. And the first part, the first requirement of those 3 requirements in the definition of measuring says that we should always send 0 to 0. So that's what f sub 1 does. But when we look at a successor, we want to know where a successor should go. We look at the value of, well, we want to know where a successor of a goes. We should look at the value of a, not under f sub 1, but under the previous guy, f sub 0, and then add 1. So if we do that, we know that we already calculated that all of everything is sent to 0 by f sub 0. So this is 0. So this is sent to 1. Okay, so f sub 1 sends 0 to 0 and everything else to 1. Then similarly, we can do all the other calculations. F sub 2 sends 0 to 0, 1 to 1, and everything else to 2. So it sends, so f sub, let me see if I can get this right, f sub n of m sends that to the min of n and m. Okay, and as we saw on the previous slide, f sub infinity is just going to do, I don't want to say the identity because these two things are not the same, but it does kind of the identity in some sense, that it sends the n of the natural numbers here to the n of a, by which I mean the nth successor of the special point in a. Okay, so these are the elements of this Hom coalgebra. And now I hope that a few times I've used the word partial for the elements of this coalgebra maybe start to make sense, because this guy here is an algebra homomorphism from n to a. And these previous guys are like some inductive building up of that algebra homomorphism that themselves are not algebra homomorphisms, but are part of the way there. So I want to call them partial algebra homomorphisms. Okay, so let's do another calculation. Like I said, I want to call these partial and partial algebra homomorphisms. But I want to do in the next slide another calculation that's slightly more complicated to give a slightly more grip onto what's happening. So in the previous slide, I was looking at the relationship, or like the Hom coalgebra, from the natural numbers, the initial algebra, to an arbitrary algebra A. Now I want to consider, in my mind, just like slightly more complicated, like the next most complicated thing I can think of to put in for the first algebra. So not the initial one, which is the most simple in some sense, but let's consider these algebras, which are quotients of the natural numbers, where we just identify everything after some number n. Okay, so they inherit an algebra structure from the natural numbers that sounds like 0 to 1 and 1 to 2, et cetera, and then n to n over and over again. Okay, and dually, we have dual, analogous coalgebras, they're subcoalgebras, subterminal coalgebras of this guy. So we can consider these ones that have this underlying set, so all the natural numbers between 0 and n, and that inherits a coalgebra structure from the fact that this is a subset of this set. So we send n to n minus 1, and then to n minus 2, and et cetera, to 0, and then when we try to send 0 somewhere, that's just undefined. Okay, so those are the algebra and coalgebra structures on these kind of second most basic algebras and coalgebras. Now we want to calculate the algebra, well, homomorphisms first, as I have written here, and then the coalgebra, the universal measuring coalgebra between them. Okay, so if we think about it a little bit, and we just wonder to what extent there are algebra homomorphisms from an algebra like this to an arbitrary algebra A, then there's exactly one. Indeed, it's like it's a factor of the unique morphism from the natural numbers to A. If I want to say A has the same kind of relation that defines little n. So if we look at the nth and the nth successor of the base point in A, and they're all equal for everything bigger than n. And if A does not have this kind of relation, then there's no possible algebra homomorphism. They don't line up. Okay, so now I'm just going to pull it out of my hat again, this calculation in the enriched case of what this universal measuring coalgebra is between n and A. So similarly to the previous case where we had capital N here, when we do have an algebra homomorphism, we find that the value here is n infinity. And again, we can recover this from this calculation. We can recover this calculation by looking at the set-like elements of n infinity, and that's just the point at infinity. So that's represented by this guy. But now we're here, here, like the question is there an algebra homomorphism from n to A just gets like a yes or a no answer. Here we get yes, and here we get no, but kind of a reason why there's no algebra homomorphism. So I want to argue that that's kind of the extra information that this category, this enriched category is carrying. When the answer is no, we get just not no, but this coalgebra, which is telling us where an attempt to build up an algebra homomorphism fails. I'm just wondering if I have, okay, I didn't add any explanation about this, so I'll just say in words. So if we think about the previous slide, let me actually go back to the previous slide. So here we're kind of inductively, in some sense, building up this algebra homomorphism that always exists from the initial algebra n to A. And what's happening in the slide after this is that this kind of inductive process is going to fail exactly at n when A doesn't have this kind of relation. So then we find this answer here is telling us, yeah, you can construct f sub 0, you can construct f sub 1, etc., etc. You can construct f sub n, but you cannot construct f sub n plus 1. That's where it fails. Okay, so yeah, so I want to say that this category, the enriched HOMs, the universal measuring coalgebras, are telling us to what extent there's an algebra homomorphism between the two algebras that we plug in. Okay, so what can we do with this? So classically, Wheeler and other people have done a lot of interesting stuff with this, but in our case, we're interested in semantics of functional programming languages. And when you do that, you are often interested in inductive data types. And so in particular, the initial algebras of particular endofunctors that we're calling, that are usually called polynomial endofunctors. So, I mean, I guess so far in the talk, I've just used the initial algebra, my favorite example, which is the natural numbers, to do some calculations, to serve as a useful object in that category that's easy to do calculations with. And now I want to generalize the notion of initial object in order to generalize the notion of inductive data type. Okay, so in category theory, there are many, many equivalent definitions of initial object that one might think of. So we thought of a lot of them and tried to generalize all of them, and this was the one that admitted the best generalization. So we want to think of an initial object, like in the null sense, to be an object A, such that for all other objects B, there's a unique morphism from the terminal set to this set of morphisms from A to B. Okay, so by writing the definition of initial algebra in this way, I've exposed this thing that I might make into a parameter and change. So this is, maybe I can say quickly that this is inspired by the notion of weighted limit or colimit, but it's not exactly the same. Okay, so I expose this singleton just like kind of in the theory of weighted limits, and then I change it to an arbitrary coalgebra. Maybe I can also say that if I do this in a normal category, nothing interesting happens. But now in this enriched category, I change this parameter to an arbitrary coalgebra C. And then I can define a C initial algebra to be an algebra A, such that for all other algebras B, there's a unique morphism like this. Okay, so now I will just give the results of some calculations, especially in our favorite example. So for the natural numbers endofunctor, we find that n is the I initial algebra and also the n infinity initial algebra. And maybe I will say some words right now about what's actually going on here. So in the previous slides where I was calculating the Hom coalgebra, the universal measuring coalgebra, and sometimes I was starting with algebras and I was calculating a coalgebra. Now I want to go backwards. I want to plug in a coalgebra and calculate out what is the initial algebra with respect to that. So I'm kind of going the other way. So in the previous slides, I was talking about how the inhabitants of the Hom coalgebra seem to me like partial algebra homomorphisms. And so now I want to say that since we saw in those previous slides that I, which was kind of representing, at least in the context of the Hom coalgebras, the particular elements that represented total algebra homomorphisms, that when I make a statement like this, I kind of want to interpret it as saying that n is the initial algebra with respect to total algebra homomorphisms. And similarly, we saw that it's really the point at infinity that's important in the calculation of the Hom coalgebras that produce at infinity, and that we have all these other functions that were kind of building up that total algebra homomorphism. So similarly, I might think that this coalgebra is also kind of describing for us total algebra homomorphisms. And so again, this is just kind of the same statement in different words, that n is the initial algebra with respect to total algebra homomorphisms. Okay, but now if I plug in something more interesting, if I plug in one of these coalgebras, that's just the set from 0 to n with the kind of standard coalgebra structure, I do find that this algebra little n is the n dual initial algebra. And I'm interpreting this mathematical statement internally as a human as saying that this guy is initial with respect to n partial algebra homomorphisms. Okay, so that was the theory. Now I've worked through some aspects of one example, the natural numbers example, which is pertaining to a particular endofunctor. And you might have noticed that in the beginning, we're saying that on these endofunctors, you need to assume that there's some extra algebraic structure, but I didn't talk about that at all for this particular example. And that's because this particular example is so simple that the algebraic structure we need is there trivially. So what we need really is a monoid structure on the singleton that we're adding. So we're doing x plus 1, and that of course is there trivially. So now I want to just say quickly what all the examples are, at least the ones that we thought of. So we have always the identity endofunctor, but it's not something very interesting. When we have a constant endofunctor, then we need a commutative monoid structure on the value there, a. If we have two instances of this list of examples, if I'm generating all the examples, then we can compose them and find an endofunctor that satisfies our hypotheses. If our underlying category is closed, which I guess I have been assuming for this whole talk, then the pointwise tensor of two examples is still an example. The coproduct is an example if we have a functor f and a kind of f module functor g. And then we have the exponential. We have W type, which kind of generalizes these, I would say, without reading through it very carefully. And interestingly, nice example that we found in the literature is the discrete equational systems of Leinster, where they were looking at actually a co-Cartesian monodal structure. Okay, so those are the examples. I'm now going to talk about work in progress. So are there any questions before I transition? Okay, so yeah, I want to say that I had this slide that showed there are many, many instances of this general phenomenon. So one question is there a general theorem of which these or most of these are all instances? That's not really what I'm talking about in this section. In this section, I'm talking about maybe a similar question, which is like, how far can I actually push the situation that we're working in this paper or these papers? Okay, so let's think about like what is actually happening to make this theorem go through, and how far can I push the boundaries out of this theorem? Okay, so I in the let's say the main body, the middle section of this talk, I just explained the main theorem by working through an example and doing some calculations. Now I want to talk about what is happening in the proof of the theorem. Okay, so in the proof of the theorem, we describe by hand this kind of cotensor of the algebras over the coalgebras. So we construct by hand a functor like this, and it takes a coalgebra and an algebra, and it produces an algebra structure on the internal Hom. So we're again assuming that the underlying category is monodal flows. So we put an algebra structure on the internal Hom from the underlying object of C to the underlying object of A. So how do we do that? So we do this basically, which I'm gonna walk through. So algebra structure means a morphism from this guy to this guy. So we do that by composing these two morphisms. So we use the lax monoidality of F to push this F inside this internal Hom. That's just the definition basically. And then we pre and post compose by the alpha and the chi that are the coalgebra and the algebra structures to get back to the C and the A. Okay, so that's how we define this functor. And then basically we just use the the adjoint functor theorem to just switch some of these categories around. And we take some ops, I guess. And then we arrive at a functor like this that gives us the enrichment of algebras and coalgebras. Okay, so how can we generalize this? This is the basic move that's being made in our paper and all the other papers. Okay, so what can you do? So first you can think maybe about dialgebras, which I only learned about by thinking about how to generalize this. So a dialgebra is a pair of, first I should say, for a dialgebra, we need two endofunctors, or let's say they could be two functors, two parallel functors. And a dialgebra is an object in the domain X and a morphism from Fx to Gx. So if G is the identity and F is also an endofunctor, then this is an algebra, and a dialgebra is an algebra. And if F is the identity and G is also then going to be an endofunctor, then this is a coalgebra. So dialgebras generalize algebras and coalgebras. We use the identity for one of F or G. And so we can think about if we can play the same game with just now arbitrary dialgebras, where we're not assuming that one of the functors is the identity. And indeed, we find that with some hypotheses here, that FG dialgebras are enriched in GF algebras. So the statement of our original paper is that that F id dialgebras, aka algebras, are enriched in id F dialgebras, aka coalgebras. Okay, so how do we do that? So we do basically the same thing that we did in the previous slide in our paper. So a dialgebra structure on this internal Hom is a morphism from this guy to this guy. So we get that by first pushing the F inside, using the fact that F is lax symmetric monoidal. Then we pre and post compose again by the algebra the two dialgebra structures to get this. And then we pull the G outside by using the fact that G is colax monoidal. Okay, and then, sorry, I'll go back. And then we find, this has to be written down very precisely, but seems like a clear generalization that we find that the FG dialgebras are enriched in GF dialgebras. Okay, but why does this X have to be the same? So a second ago, I just said, why does one of these functors have to be identity? Now I ask, why does this X that appears here twice, why does this have to be the same? Okay, so we can think about common categories, which is the situation where we don't require that the two appearances of X are the same. So now we're looking at functors that don't have to be parallel, but should have the same codomain. So two functors f and g, both into E. And now we find, for this same reason, that the common category of f over g is enriched in the common category of g over f. Okay, and then there are interesting questions, like you can encode like cones and cocones into common categories, and then you find some enrichment there. The only problem, I think, that is really the content of the future work that might come out of this slide is not like the formal proof of this, which seems fairly straightforward, but instances of these enriched categories that are actually telling you something useful. Okay, so yeah, and then maybe where else can we go is the question. Okay, so that's really it for the content of my talk. So just in summary, we have that algebras are enriched in coalgebras. We have a lot of hypotheses, but then we have an interpretation of what this additional information is that the enriched category is carrying in terms of partial algebra homomorphism. We have many examples, even though we need extra hypotheses or a lot of hypotheses. And then we try to give kind of like a use case of this theoretical work, which is the more refined notion of initial algebra. And then we're looking for generalizations. Maybe I should also reiterate that in the context of this hottest seminar, obvious question is also, what is the corresponding theorem for higher inductive types? I mean, certainly higher inductive types are enriched in higher co-inductive types, but to write that down precisely would be difficult, I think. And okay, that's it. Thanks.
Great. We'll have our traditional silent applause. And thanks for that very clear talk. Who has a question? Please go ahead. Sorry, Joseph, if you want to ask a question, please go ahead.
That was a very nice talk. I have maybe two questions. One is, have you thought about the version where it's like a monad algebras enriched in coalgebras of something? So for example, if you have like a Levier algebraic theory, and then like, for example, the theory of groups, and then we have like co-groups in the category of groups, they're like the free groups. And then is there like a enrichment there?
Yeah, so okay, so you asked about monads first, right?
Yeah. I guess it's like part of the same question, like I guess the monad would be, or for groups, it would be like the free group.
Yeah. So I haven't thought about like this, the second part of your question about these monads and comonads that might come in pairs. But in our paper, it's really just about endofunctors. We don't say anything about monads, but we do have a theorem about like one monad, the algebras for one endofunctor being enriched in the coalgebras for a different endofunctor, assuming some connection, some algebraic structure between the two endofunctors. And with other people, like in particular, well, with my co-authors and with Richard Garner, we've thought a little bit about how to upgrade that to a theorem that says that the algebras for a monad are enriched in coalgebras for a comonad with some kind of algebraic structure relating the monad and the comonad. So that should certainly, I mean, I expect that to be doable, but I haven't given any thought to your question about like groups and co-groups, but that's an interesting question.
Okay, thank you. And there's like actually also a separate question, which is like, does the sort of C indexed initial condition correspond to some like homotopy initial algebra at all? Is that something you could do? Because that's something that comes up when I was trying to formalize like a higher inductive type. I don't know if that's could be done as a special case of this.
Yeah, that's an interesting question. I mean, they okay, just intuitively, they seem different in the sense that the C initial algebras, I want to say like that. Yeah, it's not initial in some weak way. It's kind of initial where I just like cut off some of the category actually. There's some there might be some analogues or some more precise connections I haven't worked out yet with previous work where they actually try to obtain the same things by looking at initial objects of subcategories. So it's kind of like, yeah, you want to kind of cut out some of the category and take the initial object in some sense. But it is a good point, which is why I spent some seconds thinking about it, that maybe that there is a connection with the homotopy initial things, or yeah, something more interesting. I mean, certainly like there doesn't seem to be, I mean, the initial algebras or the C initial algebras I have here aren't an instance of weighted limits or colimits, but I'm kind of thinking of initial things as a limit of the whole category. Yeah, so I don't know the connection. I don't know of a precise connection with like normal weaker notions or enriched notions of initial objects.
Okay, thank you.
Yeah, but another very good question.
So I'll ask a question from the chat. Is there a dual known to all of this, i.e. coalgebras being enriched in algebras?
Yeah. Yeah, so that's something that I think we don't understand very well. I mean, at least I don't, probably not that complicated, but so the generalization I was talking about, maybe I should say on those slides, was kind of a dual notion, right? Because I said, okay, the FG dialgebras are enriched in GF dialgebras. If I just replace one of them with the identity, then I recover the original theorem. So I just could have replaced the other one with the identity, and then I see that coalgebras are enriched in algebras. So in that kind of sketch that I was giving at the end, I was just assuming, okay, I have all the adjoints I could possibly want, like just assume adjoints everywhere. But for our original theorem, which is the one we have written down precisely, we assume that the underlying category is locally presentable. And that is notoriously difficult to dualize in the sense that there aren't any examples. There are very many examples. So the way that we've constructed this, the way that we've written down this theorem, we can't really dualize it. I mean, at least with any examples, because of this hypothesis of being locally presentable. But I think if we just thought more clearly about what actually we need, like I heard recently about a concept called total categories, which is dualizable, what we actually need to get all these adjoints, I mean, maybe we just assume that we have all the adjoints and we can find that in examples. That seems doable. Yeah, so there is a dual statement, but in our paper, and I think actually in most of the other papers that I mentioned, people are assuming local presentability, but it's hard to dualize.
Maybe I could ask a follow-up, because I was going to ask this already. Exactly the highlighted hypothesis, locally presentable and also the accessible. You know, how much do you think you can get away from them? They're very non-constructive, right? They just, the adjoint functor theorem just pops out this object.
Yeah.
Is there much hope of actually just giving a construction in certain cases, or having some other hypotheses that would work?
I guess the thing that for me is kind of fuzzy in my mind that I'm not so much an expert in, but one of my co-authors, Maximilien Péroux, is probably more of an expert in. Is so we're using the hypotheses of the underlying category being locally presentable and the endofunctor being accessible, and hard-hitting theorems by like Adamek and Rosicki and people like that to say that the category of algebras and the category of coalgebras are also locally presentable, and therefore they have all the limits and co-limits and adjoints that you could possibly want. So yeah, I've done a little bit of digging to find, like, I heard about this notion of total category, which basically also gives you all the limits, co-limits, and adjoints you could possibly want that is actually dualizable, in the sense that there are examples of co-total categories and a little easier to work with, maybe, except I don't know of any work that shows that under some hypotheses, like if your underlying category is total, then your category of algebras and coalgebras is also total. Maybe I would just have to do that myself, but yeah. So so this is kind of the categorical machinery that we're using, that people in the past have given us a very easy recipe to see that the category of algebras and coalgebras are locally presentable, meaning that they have all the limits, co-limits, and adjoints that we want. And I would say, like, I wouldn't see how to give a direct construction that's not in terms of like limits or co-limits. So I need something like that, I think, on the category of algebras and coalgebras. Yeah, so that's something that needs to be investigated, I think.
Okay, thank you.
Okay, if there are no further questions, I think let's thank Paige again with another round of silent applause.
Thanks.
Great, and we will be back sometime in 2025. So enjoy the holiday break.